Okay, hello. 10 more minutes to go over just the end of this packet on sequences. Let's go. On limits of sequences. I believe we stopped with 25. I think I even said the answers to 27, 29, and 30 out loud, and there sort of wasn't much to say, maybe. So the limit as n goes to infinity of the log of the secant of 1 over n. What is that? Well, secant, we know what secant looks like at 0. It looks like that. So as n goes to infinity, then 1 over n goes to 0. So you're taking the secant of a number which is very, very close to 0, which is going to give you 1. So this is like the log of the secant of basically a tiny positive number, and the secant of a tiny positive number is pretty much going to be 1. In fact, it's going to be a tiny bit more than 1. And the log of 1 is going to 0, because that's just a fact about logarithms. Okay, and then 29 and 30, I think, are also relatively straightforward. This is the limit as n goes to infinity of root n plus 1 over root n minus 1. What can we say about this? Well, it's pretty clear that this is just going to be 1. Maybe the best thing to do is to put the whole thing inside one big square root. So this is the square root of n plus 1 over n minus 1. And then, kind of inside there, we can divide the top and bottom by 1. This would be maybe the most organized thing to do. So that would give you 1. That would give you 1 plus 1 over n over 1 minus 1 over n. And so since since this is going to 0 and this is going to 0, you get something that looks kind of like 1 over 1. That's 1. Square root of 1 is 1. So okay, done. And for 30, it's pretty much the same thing. I'm taking the limit as n goes to infinity of the cube root of 8n squared minus 5n plus 1 over the cube root of n squared plus 7n minus 3. So maybe the best thing to do here is to write this as one big cube root, and so we get 8n squared minus 5n plus 1 over n squared plus 7n minus 3, and then we use our knowledge of how to deal with rational functions to deal with the inside of this cube root. And okay, here what I would do is to divide the top and bottom by n squared. And so we get the limit as n goes to infinity of the cube root of 8 plus 5 over n plus 1 over n squared over 1 plus 7 over n minus 3 over n squared. And now this is going to 0, this is going to 0, this is going to 0, and this is going to 0 as n goes to infinity. So this is just the cube root of 8 over 1, and so the answer is just 2. Okay, those were sort of easy. Maybe we didn't need to do them at all. Let's go to these kind of E problems. So, all right, I can't know exactly how much you've retained from last year about E. So for now, let me just pretend that you all completely remember that E is this number, which is defined to be the limit as n goes to infinity of 1 plus 1 over n to the n. And alright, I'm going to actually make a video all about this. But for now, somewhat out of sequence, let's just take that. Okay, well, then the problem just tells you this number 33 just tells you basically exactly what to do. They say, okay, what if I was presented with the following limit? The limit as n goes to infinity of 1 plus 2 over n to the n. Well, that looks a lot like e, but there's this little kind of 2 here. And there are a couple of different options. Actually, sort of what I might, okay, so what the book tells you to do is do some sort of algebra, gymnastics or something, and rewrite 2 over n as 1 over n over 2. Alright, I can do that, that's certainly just true. And then let's rewrite n as n over 2 times 2. Why would I do that? Well, what these people are essentially suggesting you do is kind of change the variable. And so the person who wrote this packet now wants you to think of n over 2 as like the variable. In other words, maybe it's better if we make an explicit substitution. So let m, say, be n over 2. Now, as n goes to infinity, I think it's clear that m also goes to infinity. And so, let's now take this limit that we're trying to calculate and rewrite it in terms of m's. Okay, in other words, let's rewrite it as the limit as m goes to infinity of 1 plus 1 over m to the m times 2. Why would I do that? Well, this is now e, almost. All I have to do is use some exponent rules here to remember that if you're taking something to the m times 2, you can think of that as, to the m to the 2, like that. And if you want to be even more kind of fancy and sort of particular about writing every single step, then what you could do, and hopefully you'll agree that this is like kind of reasonable or something, is, well, maybe this is kind of overkill. Ultimately, what do I know? I know that as m goes to infinity, 1 plus 1 over m to the m is going to e. And so this whole thing is just going to e squared. And that's just actually, I think they just tell you that, right, in the packet? No, not quite. They do everything up until the last minute. But then, yeah, that's what is e squared? It's some number, 7 point whatever. Okay, and then 34, they just want you to do this 2 more times. So 34a says, hey, once again, building on this knowledge and understanding that the number e was defined as the limit of a sequence, and maybe you have that understanding, and maybe you don't. I'm still going to just go over these problems right now. Take the limit as n goes to infinity of 1 plus 3 over n to the n. What's up with that? Well, you just pull the exact same trick again, right? You rewrite this as the limit as n goes to infinity of 1 plus 1 over, instead of 3 over n, you write it as n over 3. And then instead of n, you're going to write that as n over 3. And let's just do it sort of all at once, to the 3. Why is this, well, certainly this is algebraically equivalent. Why is this a good thing to do? Because now, if I let m be like n over 3, say, then this is the limit, as n goes to infinity, of 1 plus 1 over m to the m, but then that entire thing cubed. And everything inside the brackets, as m goes to infinity, becomes e. So the answer to this is e cubed. That was 34a, and 34b I think is similar, but with maybe like an extra twist. Now we have the limit as n goes to infinity of 1 plus 1 over 2n to the n. And now I guess the thing to do is to rewrite this as the limit as n goes to infinity of 1 plus 1 over, I kind of already just want it like that, but for n, I will rewrite n as 2n times 1/2. Or maybe even just in the spirit of doing it all in one big step, to the 1/2. So by exponent rules, something to the 2n to the 1/2 is something to the 2n times 1/2, so I haven't changed this at all. But now, if I let m be 2n, well, it's still true that as n approaches infinity, m will also approach infinity. And so I may rewrite this limit as the limit as m goes to infinity of 1 plus 1 over m to the m, but all to the 1/2. And so as m goes to infinity, that becomes e inside there, and so this whole thing is e to the 1/2 or square root of e. Okay, good. Let's wrap this up by doing these so-called calculator problems. I think this is such an old textbook that they might refer to them, what are they called? Calculator exercises. But of course, you would probably just do this on a computer or something. Well, anyway, let's just do 2 and 3. I think they're both kind of interesting. Here's what it says, and maybe I don't need a calculator even, but maybe I do. T1 equals 1, and here this sequence is being presented to me recursively. T sub n is T sub n minus 1 over 2 plus 1 over T to the n minus 1. Okay, so suppose I know nothing whatsoever about the sequence. What do they want you to do? You know, not much, right? Crank it out with a calculator and then just guess what you think the limit is. Okay, so let's maybe expand this directive a little bit and try to see what's going on. Let's see how much I can get away with doing this in my head. This is 1. What's T2? Well, T2 would be 1/2. Sure. 1/2 plus 1. So that maybe I want to do it something like, maybe I'll kind of do my scratch work over here or something. So so the first term of the sequence is 1. What's T2? T2 is the previous term, which is 1 over 2, plus 1 over the previous term. So that's just 3/2. Okay, great. I can probably get by with some fractions. So what's T3? Well, T3 is, according to this recursive rule, the previous term, so that's 3/2 over 2 plus 1 over plus 1 over 3/2. All right, so I see why this is kind of annoying. This is 3/4 plus 2/3, and if you do this with the calculator, you know, it's just easier or something. So yeah, common, what is that? 9 and 8, 17/12. Probably did that right. So 17/12. So 1 and 5/12. So 1.4 something. Okay, let's do maybe like one more. What's T4? Well, it's the previous term T3. So 17/12 over 2 plus 1 over 17/12. So man, I really don't want to do this because that's 17 over 24 plus 12 over 17. 17 is prime, so like there's just no good way to do this except doing it, right? That's like 288 and 289. Hopefully that's true. Yeah, 170 and 49. Sorry, what? 170 and 70, 240 and 49. Yeah, that is 17 squared. And then that's, what is that? 1 for 288. Okay, so that's 288 over 17 times 24, which is something. I have no idea. Anyway, 240 and, I don't know. I'm just going to write 24 times 17. Okay, this is just a waste of time. This is 577 over, so I see why this is a calculator problem now. So 577 over 408. But, first of all, I'm not even confident that I did that right. And I'm definitely not going to do any more of those. But, alright, just kind of going through this one more time. Oh man. 57048. Yeah, 577 divided by 408 equals 1.4142. Alright, so you should all be experienced enough with kind of mathematics to recognize that something is going on here. What is 1.4142 blah 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 blah? I think that this is the square root of 2. So actually that is kind of amazing. Using now the language of limits, this is the second time this has happened. In the first video I recorded earlier this week of a problem that you did a week and a half ago, before we learned limits, we saw some sequence whose limit appeared to be phi. Here, it appears that the limit, as n approaches infinity, of this sequence, it appears that this is root 2. So I'm not positive that this is true, and I'm very confused about why this should be true. And the nature of this calculator exercise is, hey, here's a cute little thing that happened. Don't worry about why. Just bask in the mystery of mathematics or something like that. No, I think we can actually understand this. So what I'm not going to do right now is to prove to you that this sequence has a limit. I am going to just take it for granted that the terms of this sequence are going somewhere. But I will now prove to you that on the assumption that this sequence has a limit, that this limit is root 2. Okay, so all right, so let's just grant me for the minute that the limit as n goes to infinity of this sequence is indeed exists, and so it must be like L. Okay, well, why should we expect, or why should we think that the limit of the sequence is root 2? Well, as I was saying in the previous video, think because this sequence is defined recursively, what it means for this sequence to have limit 2 is that the terms are getting really, really, really close to root 2. And so, if the terms are getting really close to root 2, once you go out to like the millionth term or something like that, then the terms barely differ from each other. They're essentially the same number. And so, since this sequence was defined recursively, what does it mean to say that this? Then what we mean is like the sequence is sort of the terms are barely changing. So what we would expect, for example, is that for sufficiently large n, that the n plus first term is essentially just equal to the nth term, okay? Which would also just be equal to L. That's what it means for this sequence to have a limit. That when you perform this recursive rule to generate the next sequence from the previous one, that it's just the same thing again. Okay, so in other words, if on the assumption that this sequence has a limit and that the limit is the number L, what is L? Well, L must be a number such that when you add that number over 2 plus 1 over that number, what you get is basically L again. In other words, this is say this is the this is what I'm calculating here is the nth term, right? So this is like the nth term, and this is like the n plus first term. So what this equation is basically saying is, hey, L is a number such that when I generate the n plus first term, it's basically just equal to the nth term, which is to say that these are barely changing. Okay, I'm going too slow here. Well, now I can just solve this equation, right? Subtract L over 2 from both sides. You get L over 2 is approximately 1 over L. And solving this equation, well, that's just L squared is 2. And so, in fact, so root 2 is the unique number, which is equal to its own self over 2 plus its reciprocal. And so that sort of explains why the limit of this sequence is root 2. Okay, last one. We'll do this number 3, and it has a similar kind of exciting aspect to it. Here we go. They say, okay, well, the question is, what is the square root of 1 plus 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 this is like, what should this be? Okay, well, you might be, if you're a sort of careful thinker, you might be very spooked out by this kind of infinite cascading, dots, like that's very kind of scary. So, says the paper, no, it's okay, we got this. Let's do like a mathematician thing, which is to say we don't have to deal with infinity directly. Let's deal with infinity indirectly by considering the sequence. And what is the sequence? Well, it looks like this. The first term of the sequence is root 1 plus root 1. The next term of the sequence is root 1 plus root 1 plus root 1. Plus root 1. The next term of the sequence is root 1 plus root 1 plus root 1 plus root 1, etc., etc. Okay, so that's a sequence. Every single term in that sequence is completely understandable and completely finite and is a legitimate number, but the sequence itself goes on to infinity. And so instead of asking what this equals, we can ask a more precise question, which is, does this sequence have a limit? And if it does, what is it? And whatever it turns out that the limit of this sequence is, we can reasonably interpret that as the value of this kind of infinite expression. Okay, and it's beyond our ability right now to prove that this sequence has a limit. So once again, all they ask you to do on this paper is to just plug it into your calculator and kind of just see what happens and just smirk and just be like, woo, that was exciting. And we're not going to do much more than that. I'm not even going to use my calculator here. But it does, when you do this out a whole bunch of times, you start getting this like 1.61 thing, 1.618. And so could it be that this sequence, this is number 3, could it be that this sequence has a limit, and could it be that the limit of this sequence is in fact the golden ratio phi? Yes. How can we show this to be true, or how can we understand why this is true? Well, it's the exact same logic as the previous problem. I'm not going to prove to you that the sequence has a limit, but suppose that this sequence does have a limit, and let's suppose that it's L. Okay. I'm going to show you that L has to be phi. Why? Because if you go out far enough in the sequence, then the terms are going to be barely distinguishable from each other. And so, how do you get from one term to the next? I probably should have written this already. Right? The first term of this sequence, to write it out a little bit more carefully, is just like root 2, right? The first term of the sequence is just root 2, but the nth term of the sequence is just the square root of 1 plus the previous term. So here is a recursive rule for generating, one term from the next term, right? You just take the previous term and you wrap it in a root 1 plus type situation. Okay, well, if that's the case, then L must satisfy the condition that that when I take the square root of 1 plus L, what I get back again is basically L. Because that's how I generate the next term. I take the previous term, L, I add 1 to it, I take the square root of that. And that's how I get, the next term. But if this sequence has a limit, then the next term is basically just equal to the previous term, L. Okay, so solve this equation. Well, you get 1 plus L equals L squared. And that is precisely minus L minus 1. Now we have a quadratic equation, and the solution to this quadratic equation is phi, the golden ratio, 1 plus root 5 over 2. So I think that's exciting. I don't think it was too hard to see this. And okay, this is actually a preview of something you're going to be doing like almost exactly a year from now in Analysis 1B. You will be learning some more advanced topics which enable you to prove kind of precisely that that this sequence does have a limit, but that's kind of calculus. Okay, goodbye.